So in this video we're going to cover space trusses and how you can determine the forces within each of the members of a space truss. So the simplest case of a space truss is if you have 6 members connected in a tetrahedron fashion. So a tetrahedron. Alright, so the simplest example of a space truss is drawn on the left hand side. Space trusses are typically found in supporting structures, such as they're used a lot in roofs, and they're used a lot in electrical transmission towers, so like high voltage power lines. Alright, typically they have very low weight, and very strong for their weight, so that's the advantage of using a space truss. So the simplest case for so space trusses, even though they're in 3 dimensions, you can use the same analysis procedures as we have done in 2D. Alright, so we can still use the method of joints, and we can still use the method of sections. Alright. Alright. So space trusses follow the same critical assumptions as 2D planar trusses. So you can consider a structure to be a space truss if all the members within the truss are considered 2-force members, meaning that they're either going to be in tension or they will be in compression. Alright, so you can consider a structure a space truss if all the forces applied to the truss are at the joints, and then all the joints of the space truss are considered ball and socket joints. So these two assumptions are valid if all the members on a truss, even if they are welded or bolted together, intersect at a common point, or they're concurrent, and then if you can neglect the weight of the members. Right? There may be some cases where the weight of the members, you can't neglect it, but to get around that, what you can do is you can apply half of the magnitude of each member's weight at the end of the joints, right, or at the end of the members. Right. So very similar assumptions to what we made in for 2D trusses, except now instead of having pins at each of the connections, we have ball and socket joints. All right. So like I mentioned earlier, you can use either the method of sections or you can use the method of joints. Either method is fine to use. So for the method of joints, it's just the same process. You apply the equilibrium equations. So in 2D, we had some of the forces in the x and some of the forces in the y. In 3D, we're just adding this new equation here. All right. So when you're using the method of joints, you should start your analysis at a joint with at least 1 known force and at most 3 unknown forces. All right. So in 2D, we could solve for only 2 unknown forces, but now since we have a third equilibrium equation, we can solve for a third unknown force. All right. And sometimes the 3D geometry might be pretty hard to visualize, so you might want to break your forces down into their Cartesian vectors and add them all up to determine the resultant force. All right. So the second option is the method of sections. So for the method of sections, you'll cut your truss into 2 separate sections, just like you did in 2D, and then you can say that in order for the truss to be in equilibrium, they must satisfy these equations here. All right, but we have 3 additional equilibrium equations because we're now dealing with a 3D rigid body instead of a 2D rigid body, and you follow the same exact procedure once you take that section cut. So very similar to the 2D method. It's just going to be a little bit more, you just have more equations to solve for. All right. All right. And that concludes this video on space trusses.